So the second speaker is Wonyong Jang at KAIST, and he's going to tell us about on the finite freeness of the groups generated by two parabolic matrices. Please start.
네. Thank you for introducing me and giving me a chance to talk here the nice conference. In this talk, I will discuss the freeness problem for groups generated by two non-commuting parabolic matrices. This is joint work with KyeongRo Kim at Seoul National University. Here is the outline of my talk. First, I will introduce background and known result and state our main theorem. Next, I will introduce two main ingredients for proving main theorem. The first one is generalized paragraph gamma alpha. And next, I will introduce the orbit test for non-freeness. And lastly, I will give a short sketch of proof for main theorem. We start with the following basic observation. We see that matrix M in SL to C is parabolic if its trace is either 2 or -2. Then suppose we are given two non-commuting matrices X and Y with trace is +2, then we can use conjugation to show that the group generated by two matrices is isomorphic to group generated by two following specific matrices 1, 1, 0, 1 and 1, 0, alpha 1 for some complex number alpha. We denote this subgroup by G alpha. Then the group G alpha is important in Kleinian group theory. And one of the specific example is Rayleigh slice. The definition of Rayleigh slice is the subset of the complex number alpha, a complex plane C, satisfying the first condition is G alpha is Kleinian group. So it means that G alpha is discrete. And one more condition is non-empty regular set. And the second condition is, yes, a regular set is the complement of the limit set. So we can consider the following quotient space. So the last condition is the quotient space is four-function sphere. Yeah, here is the Rayleigh slice. Recall that Rayleigh slice is outside of I. So yeah. So Rayleigh slice is this region. And it is known that if complex number alpha is in the Rayleigh slice, then the group G alpha is linked to free groups. So from this fact, we may wonder if determine when the group G alpha is linked to free group. And one of the main purposes of this question is to understand the complement of the Rayleigh slice. Now, I give a basic definition. We say that a complex number alpha is free if the corresponding group G alpha is linked to free group. If not, we say that alpha is a relation number. So complex number is either free or relation. Actually, almost all numbers are free because the first reason is if its absolute value is bigger than or equal to 4, then it is known that alpha is free. And actually, if alpha is 10 second number, then alpha is free. So from this fact, we can conclude that almost all complex numbers are free. But yes, actually there are many, infinitely many numbers known as non-free numbers. The simple example is integer 1 to 3, and recall that from 4, they are free. And some special kind of rational number are also known as relation number. For example, 1 over n, 2 over n, 3 over n, and 1 plus 1 over n, etc. And some special complex number also known as relation numbers. Surprisingly, actually the relation number is dense in the closed interval from -4 to 4. So motivated this theorem, one of the open question is the following. If alpha is rational number and its absolute value is smaller than 4, then alpha should be relation numbers. Yeah, it is one of our open question. Now, I introduce recent Kim and Kubernetes result. Kim and Kubernetes show that the rational number S over R is relation number whenever S is between 1 and 27, except for 24, and its absolute value is smaller than 4. So this result show that there are many, many rational relation numbers, but yes, because the numerator is bounded, because S is bounded, so it eventually converges to 0. As I present, this number is converges to 0 and 1 and 2. So my question is, are there any sequence of relation number in some classes which converges to relatively high numbers, in particular 4? It is my interest find some relatively large relation numbers. And yes, here is our main theorem. We can prove that we can construct a sequence of polynomial p and alpha, and satisfying each polynomial is monic and integer coefficient, and all root p and alpha are distinct real relation numbers. So actually, from the first condition, all roots are algebraic integer. And lastly, let alpha n be the maximum root of p and alpha. Then the sequence alpha n converges to 4. So it means that there exists a sequence of algebraic integer relation numbers which converges to 4. Here is a main idea for proving the main theorem. First, we define the generalized paragraph gamma alpha and prove that alpha is relation number. It means that G alpha is not linked to free groups by definition. And if and only if the graph gamma alpha is not 3. So if gamma alpha is 3, then G alpha is linked to free group. Sorry. So we define gamma alpha and we will show this fact. And second is the orbit test. It means that if G alpha orbit of 0 and infinity contains the rational number 1 over 2, then we show that the graph gamma alpha is not 3 graph. So it means that from 1, G alpha is not linked to 3 groups. And we use part 2, the orbit test, to make the polynomial P and alpha, and we show that now the polynomial P and alpha satisfy all conditions in our main theorem. And so I will briefly recall the condition. We'll check P and alpha satisfy these 3 crimes. Yes, so we define now the generalized paragraph. From now on, we'll assume alpha is real and positive. So the group G alpha is subgroup of SL to R. So also it means that G alpha acts on the circle S1, which is the global boundary of hyperbolic space H2. Let V be the set of G alpha orbit of 0 and infinity. Then we define the generalized paragraph as the follow. The graph, its vertex set is V, so it is vertex set. And we claim that there is an edge between X and Y if and only if for some G in G alpha, X is G dot 0 and Y is G dot infinity. So actually it is H2 and infinity in 0. Then we act this space, G alpha act this space and make some many point. And it is the generalized paragraph. Also, we will denote the edge between 0 and infinity by S. So in this picture, this, change. This edge is, we denote it by R. So actually, it means that if there is an edge in gamma alpha, then it should be G dot L or some G in G alpha by definition. Yes, so it is the definition of a generalized paragraph. Next, I will introduce the basic property of the generalized paragraph gamma alpha. First one is gamma alpha is connected and not locally finite. The second is the graph gamma 1 is the paragraph. So this is why we call gamma alpha the generalized paragraph. You can easily check that gamma 1 is actually paragraph. Yeah, and next is for given G in the group G alpha, then we can make the correspond path. So yeah, actually it is that looks not very clear, but I will explain more precisely later. And the last condition property is the graph gamma alpha is symmetric with respect to the geodesic R. Recall that L is H between 0 and infinity, and I also explain it more precisely later. So I will explain more precisely the third statement. Actually, it means that if we choose element G in G alpha, and suppose we can express G it as this word, then we can consider the following sequence of edges L and the first alphabet L, and from first 10 to second one, blah, 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 and this is actually G dot L. Then they form a path without backtracking. So yeah, actually it is this picture explains the proposition, and suppose yeah this is L, and since A fixed infinity, A to the 3R is this, and same with infinity. And also now consider B alpha inverse, then note that B alpha is fixed 0, so it holds. So this H and this H meet at this point. And similarly, if the word begin with B alpha some power, then there should be H such as, yes, this H and this, these two H meet at 0, and this H and this H meet some point infinity, and it same as these two things are the same because alpha fixed infinity. So in this logic, we can make a path without backtracking. And also this proposition implies that if alpha is a relation number, then the graph gamma alpha should contain a cycle. Now we'll try to prove the converse. Now assume G alpha is linked to free group, and then the following lemma is known. Yeah, actually it is not important, so I will omit. And from this lemma, we can prove the following proposition. It means that if sorry, yes, suppose sorry, G sorry, if G alpha is linked to free group, and suppose in the graph corresponding graph gamma alpha, so suppose that a path length k beginning at geodesic HL, so it is H between 0 and infinity. Then by definition of the generalized paragraph, this H is G1 dot L for some G1 and G2 dot L blah blah GK. Sorry. Yeah, we unify this notation. So G1L is same as G1L, and G2, G3, and yeah, GK dot L. Then the conclusion is that GK has length, word length is k minus 1. So I want to point out that this proposition doesn't hold when G alpha is not negative free group because it has some many relations, so it does not hold. From this proposition, yes, we can prove that gamma alpha is not 3, then G alpha is not negative free groups. Yeah, I will explain by drawing some picture. Suppose we assumption is G alpha is free. Then by proposition, we can consider the following tests: G1.L, G2.L, G3.L, blah blah GK.L, and GK plus 1 dot L is same as L, and by the previous proposition, GK plus 1 should have length model length K, but one can easily check that in this case, stabilizer L is trivial. So by these two facts, we can obtain some model relation, and it contradicts to the assumption that G alpha is negative free group. So it is contradiction. So when G alpha is free, then gamma alpha should be free graph. Yes. So oops. I have only 2 times. So yes. So we proved that the following fact, and so yeah, I will explain how can you report test. It is simple. Uh, yeah. The statement orbit test is G alpha orbit of 0 or infinity contains the rational number 1/2, then it is not 3. How can we prove? Suppose the orbit contains number 1/2, then since gamma alpha is connected, we can make some paths from infinity to 1/2. And by symmetry, yeah, I have no time, so I will not explain it, but we can, by using symmetry, we can make paths from infinity to minus 1/2. And from this calculation, we can make another path from infinity to 1/2. Yeah, we can extend this path to the path infinity to 1/2, and we can show that these two paths are different. So two different paths make some cycle. So we can conclude that gamma alpha is not 3, and so G alpha is not negative free groups. Yeah, actually, time is over. So yeah, it is a new example of rational relation numbers, and yeah, using by orbit test. And yeah, I think yeah, I will skip the construction of P and alpha, and yeah, I think it is the time to finish. So yeah, thank you for your attention.
Are there any questions for the speaker?
I have a question. So, sorry if you mentioned this, but did you say anything about what the cardinality of relation numbers is? Is that known? Like, are there countably many or uncountably many?
You mean cardinality of relation numbers?
Sorry?
Yes, cardinality should be countable because yeah, yeah. uh, the set of relation number is subset of algebraic numbers.
Okay, I see.
Yes, so algebraic number is
Yep.
countable. Yes.
Any other questions? So you found like rational numbers, right? Like converse to 4. Am I correct?
That rational number, yeah, actually algebraic integer, and yeah, next my goal is found rational relation number to convert this to 4, but yeah, I will just try.
Okay, if there are no other,
Sorry?
are there any other questions?
I have a question.
Yeah, go ahead.
Okay. I wonder if you have two complex numbers, for example, alpha1, alpha2, and with the same modular. Then I wonder if G alpha1 and G alpha2 have the same time. I mean, if G alpha1 is free of rank 2, then G alpha2, if whether G alpha2 is also a free group of rank 2. Alpha and alpha2 have the same modular, the two different complex numbers.
Sorry, I don't understand you're correct.
I mean, choose two different complex numbers, alpha1 and alpha2,
Yes,
and they are of the same modular. For example, alpha1 is 1 plus I, and alpha2 is the square 2, right? They have the same modular. And
you
then
mean
I wonder,
this and this?
yeah.
Yes.
Yeah, this is okay. And I wonder if G alpha1, if G alpha1 is free of rank 2, then then whether G alpha2 must be free of rank 2. I wonder if they're of the same type, They must be of the same type.
I was that it is false, but I yeah,
Maybe
actually,
they are
I was told
both
that
not free.
it is known. Yeah, I was told that 3i is not. Yeah, it is free, but 3 is relation. So I think it is false.
Okay. Yeah, that's right. That's right.
Are there any more questions for the speaker? Okay, if not, let's thank the speaker again.
Thank you.